Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, I welcome you all in this course on data communications and computer networks. This is our lecture number 6 of asynchronous mode of learning in phase 2. This course is being offered at Department of Computer Science, ComSats, University Islamabad, Lahore campus. So in this lecture, we'll talk about network layer services, what sort of different services network layer provides us. Then we'll talk about the forwarding protocol, means internet protocol. We'll be talking about IP addressing and then network address translation. The learning outcomes of today's lectures are to understand network layer services, to understand the working of the forwarding protocol, means internet protocol, and to understand the basics of IP addressing. There are two types of addressing, obviously, that we'll talk about. Classful addressing and classless addressing. We'll see what is the difference between the two. And we'll also try to elevate and argue the need of having network address translation. So let's talk about the network layer first. But before that, let me remind you that in the previous lectures, we have covered the transport layer in detail. So we've talked about the TCP and UDP protocols in details. We have talked about the TCP's congestion control and congestion avoidance mechanisms and different timers that are used by TCP for its operations. Then we have talked about the quality of services and further advanced topics in congestion control and congestion avoidance. Now it's time to talk about the network layer. So network layer provides us a variety of services. For example, the first very important service that network layer provides us is basically the forwarding service, or it gives us IP protocol, internet protocol, right? So this IP protocol is basically a forwarding protocol. So forwarding protocol. So router forwards a packet based on the IP address given by this internet protocol address. And we'll also be discussing, while discussing this forwarding protocol, its datagram format and how the packets are handled, what are the different handling conventions. Then the network layer provides us also a signaling protocol known as ICMP, Internet Control Message Protocol. By the way, this Internet Control Message Protocol is called signaling protocol. It's a signaling protocol that is used to report errors. And then we have different types of routing protocols at the network layer to forward data from one machine to the other machine. Before we start discussing internet protocol, let me quickly have a discussion about the packet switched networks. Since the internet is a packet switched network, so it's important that we briefly discuss this packet switched networks first. So let's talk about packet switched network. So the internet is based on packet switched networks. Internet is a packet switched network. So we have briefly talked about the packet switched networks in our previous lectures. So in packet switched network, we know this, that data is packed in packet switched network. The data is packed into packets or datagram. So the data is encapsulated, or you may call it parceled, into packets or datagram. And each packet importantly carries a destination address. And each packet carries a destination address. And most importantly, each packet is routed independently. Each packet is routed independently. This means a packet one can take a different path to reach the destination, and second packet can take altogether a new path to reach the destination. And there is a possibility that packets can arrive out of order. So this is so, and we know this. We have discussed this also at this concept at the transport layer, that packets can arrive out of order. Okay, and this is also possible that packets may not arrive at all. Packets may not arrive at all means the packet has lost, right? So you can compare such a network, means a packet switch network, with your postal system. So we can have an analogy of postal system to understand it. So for example, what happens in a postal system? What you do with the content that you want to send? Yes, so the content you want to send must be put into an envelope. So the content you want sent must be put into an envelope. Right? And what else? Yes, an envelope must have an address, right? And the envelope must be addressed. So in the case of our packet switch network, the envelope is basically the packet header. So in packet switch networks, the envelope is the packet header. And remember, we have discussed earlier that protocols are a set of rules and regulations, are rules. By rules, I mean to say it has a syntax and grammar, certain meanings. And in this case, the protocol governs, or these rules are governing communication between nodes. Right, and obviously the format of the header, is part of a protocol. So the format of a packet header is part of a protocol. Right. So for the packet forwarding on the internet, the protocol is called or is known as Internet Protocol. Right? So here, the protocol that I'm referring to is, in fact, Internet Protocol or IP, and we are interested in looking at the format of the packet header of the protocol, means the format of the IP packet header. So for packet forwarding, on the internet, the protocol is the Internet Protocol. Or IP. Right. So so this means that packet switch network, the internet is basically based on packet switch networks, where the data is backed into packets and then transmitted on the network, and the forwarding protocol is known as Internet Protocol, and we need to look at the Internet Protocol packet headers, the envelope, so to examine what are the different fields and what's the purpose of the different fields of an IP datagram header. But before we talk about the IP datagram header, let's talk about the other alternatives, because where we have this packet switch networks, there are many alternative network architectures available, right? So we have variety of alternative network architectures. So let's also talk about, in comparison to this, that what are the alternative network architectures. Okay, and by the way, these include ATM and frame relay. ATM and frame relay. This ATM and frame relay are basically circuit switch networks. So we call it virtual circuit network. So basically, there are two types of networks. So we have packet switch networks, and then we have virtual circuit networks, right? So the virtual circuit networks also use connections at the network layer. These network layer connections are obviously called virtual circuits, and these networks are called virtual circuit networks, right? And every virtual circuit network or a virtual circuit network consists of, number one, a path. right? A path between the source and destination host. And this obviously includes a series of links and routers. Number two, it has a virtual circuit number or virtual circuit numbers, one number for each link along the path. We'll see, we'll try to understand it with the help of an example in a minute. And number three, obviously there are entries in the forwarding table of a router. The forwarding table of each router. Right, try to understand it with the help of an example. And we'll also try to differentiate the packet switch network and virtual circuit network with the help of this example. So, for example, we have our machine A, and machine A is connected to router R1. Router R1 is connected to router R2. And router R2 is connected with machine B. And then there are other routers as well. So here we have router R3, and here we have router R4. So R1 is connected to R3, R3 is connected to R4, and R4 is connected to R2. Right, and let's suppose that the path that has been chosen to forward data from A to B is this. So the path is forward packet. The path is A to R1, and from R1 to R2, and from R2 to B. And let's assume that following VCs or virtual circuit numbers are assigned. So the virtual circuit numbers are, say, 1, 2, 2, 2, let's assume 3, 2. Right. So this means when a packet is forwarded from A to R1, or when a packet leaves A for R1, it has virtual circuit number 1, 2. When the packet leaves R1, the value of the virtual circuit number is 2, 2. And when the packet leaves R2 for B, the value of the virtual circuit is 3, 2. So what happens basically, in a virtual circuit is that every router needs to maintain connection state information. So all these routers needs to maintain connection state information. Okay, and so this communication happens basically in 3 steps. So step number 1 is, or 3 phases. Phase number 1 is we establish a virtual circuit, right? So virtual circuit is set up, right? So this phase is basically a setup phase, right? And then we transfer data from A to B. So this phase is called data transfer phase. And the phase number 3 is called virtual circuit teardown. After sending the packets, we terminate this connection. So what we are doing here is that, first of all, using this virtual circuit networks, we first of all establish a connection. We set up virtual circuit. For example, we have established that this is the path that all the packets will use to travel from machine A to machine B, right? And for that, the router maintains a forwarding table. Right? So in order to facilitate this, the router maintains a forwarding table. For example, we can look at the forwarding table of, say, R1 in this example. This is the forwarding table in R1. Right. So it, first of all, it has the incoming interface. Then it has incoming virtual circuit number. Then we have outgoing interface. And then we have outgoing interface, VC number, outgoing virtual circuit number. For example, in this case, the interface is 1. And what is the incoming virtual circuit number? Yes, you're right, 1, 2. And what was the outgoing interface? Let me label these for your understanding. So this is 1, this is interface 2, and this is interface 3, right? So the outgoing interface is 2, and the outgoing virtual circuit number is, 22, right? So in this way, we have many different entries against each interface to forward packets based on virtual circuit numbers. So this is how data is forwarded in virtual circuits, where we have a specific path and all the packets will follow this path, right? So for example, I have to send 3 packets, P1, P2, and P3. All packets will follow this path. So packet 1 is packet 2, and packet 3 will also take this path. But let me take the same example and talk about the packet switch network. So if this would have been, if this is a packet switch network, so what will happen? This is a possibility that packet 1, so this is P1, P1 take this path, it takes this path, and packet 2, it takes this path to reach. So this is the path taken by packet 2, right? And similarly, if there is another path between, say, R3 and R2, so I can say, so let's assume that now the packet 3 is taking this path to reach. So each packet can take independent path to reach the destination. But in virtual circuit networks, we have a specific path that the packets have to follow in order to reach the destination. And the origin of these virtual circuit networks is based on the traditional telephony, where we used actual circuits to connect telephone sets. So since we have established the fact that we need to have a forwarding protocol, that is internet protocol, to forward packets that may take different paths to reach the destination, and it's important for us to look at the envelope of this forwarding protocol, means internet protocol, means let's try to look at the header of IP datagram. And remember, before that we have talked about that an IP datagram, broadly speaking, has 2 parts. It has a header and data or payload field. and it's time to expand the header and see what are the different details what are the different fields in the packet header and what's its utility. So first of all, the first field is called a version. It identifies the IP protocol version. It's a 4-bit field, and it is used to identify the protocol version, which is IP version 4 at the moment, because this IP datagram is of IP version 4. And this helps the router to decide how it will be dealing with the IP datagram of a specific IP protocol. And then we have next 4 bits for to identify the header length. So if a header length field is there, this means the header length is not fixed, right? So usually this header length is 20 bytes. This header length is of 20 bytes if I do not make use of this options field. Right? So if I have if I'm using this options field, this means the header length can increase, but usually the header length is 20 bytes. And then we have this type of service field. Type of service field. I hope that you're familiar with this type of service field, as we have covered this in the previous lecture. This type of service field is basically, these are 8 bits, 1 byte, and first 6 bits, as you know, are used to identify these different classes of data, and last 2 bits are used for explicit congestion notifications. And then we have the length. Then we have next 16 bits to identify the total length of the IP datagram in bytes. So this includes both the header plus the data field, right? And then we have these 3 fields: 6-bit identifier that identifies the that differentiate a packet from the other using special identifier. And then we have 3 flag bits. So there are 3 flags. So we have DF flag, and then we have MF flag. DF stands for don't fragment, MF stands for more fragments, and 1 flag is result. And then we have this fragment offset field. These 3 fields are, so these 3 fields are used for fragmentation and reassembly, and I'll discuss these 3 fields in detail in a minute, right? So I'll leave it with a question mark. I'll try to cover it in the next couple of slides. And then we have this 8-bit. These 8 bits are to define TTL, time to live. Right. So this time to live is to ensure that a packet is not continuously circulating inside a network. So every time a router forwards a packet, it decrements the TTL value by 1. And if a router receives a packet with TTL value 0, it will discard this IP datagram and will send an ICMP message to the source machine telling that the packet has been, or the IP datagram has been discarded because its TTL value has expired. Okay. And then we have next 8 bits. These 8 bits are used to define which upper layer protocol to deliver the data placed inside the payload field, right? So, for example, if the value of this field is, for example, if I want to deliver it to TCP, the value is 6. If I want to deliver data to UDP, it's 17. And if it's, for example, Internet Control Message Protocol, the value is 1. So this field has its implementation similar to the port number, where the port number identifies which process to deliver the data at the application layer from the transport layer. And here, this field identifies the protocol to deliver the payload to, right? Either I'll be delivering the payload or the data in the data field of IP datagram to TCP or UDP or ICMP. And then we have 32-bit source IP address and 32-bit destination IP address. And here we have this options field, and in this options field we can use timestamps, we can record the path that is taken to reach destination, or we can list the routers that we need to visit in order to reach a specific destination. And this 16-bit, these are 16-bit internet checksum is for error detection, right? And then we have this payload field, and this payload field have a data of 65,535, right? So obviously this much amount of obviously this huge size of an IP datagram is not possible because at the data link layer the maximum transmission unit does not support this much amount of payload field. Right. So let's talk about IP fragmentation and reassembly in detail, because remember we have a question mark on these three fields to discover it in details, that how a packet is fragmented and reassembled. So let's try to understand it. Okay, so in IP fragmentation and reassembly is allowed in IP version 4, right? And this is because these different links can have different maximum transmission unit size. For example, if this link is, let's say, an Ethernet link, this means I cannot have a frame size greater than 1500 bytes, because this is what this is. We know this is the maximum transmission unit size. So if I have an Ethernet frame, its size cannot be greater than 1500 bytes. Similarly, let me assume that it's a wireless link between these two routers. This means if it is Wi-Fi or wireless fidelity, the frame size cannot be greater than 312 bytes. Right, and similarly, over a long distance communication, maybe a link cannot have data size greater than 576 bytes, right? So now let's assume that this machine, it's a sender and it's the receiver. Let's assume that this machine has generated a TCP segment of size 4,000 bytes. So this machine has generated a TCP segment of size 4,000 bytes. And let's assume that this link is an Ethernet link. So this means at maximum I can have a size of 1500 bytes. Right? So can I encapsulate this IP packet containing 4,000 or having a size of 4,000 bytes into a frame, or can I encapsulate into a frame having a maximum transmission unit of 1500 bytes? No, I cannot. So this means what? This means I need to divide this TCP, this IP datagram into 3 fragments, 3 smaller datagrams. So probably the first datagram can have a size of 1500 bytes. The remaining can also have a size of 1500 bytes, and whatever left is or will be placed in the third smaller datagram. And the reassembly is always done at the final destination. Why? Because at the final destination, the transport layer wants to have a one unified representation of TCP datagram, right, or UDP datagram. So that's why we have to do the reassembly at the receiver. So this means the fragmentation and reassembly, where it's important, where it's required, we have to divide the IP datagram into smaller segments. And for that, we need to have these three fields. 16-bit identifier, we have these flags, the don't fragment flag, more fragments flag, and then the fragment offset. Right, and let's try to understand this with the help of an example. Let's assume that the length of an IP datagram generated by the source, as was the case in the last slide. So this IP datagram has a size of or length of 4,000 bytes, and I have a link of Ethernet where the maximum transmission unit size is 1,500 bytes. So what I have to do? Yes, I have to divide this larger IP datagram into 3 smaller fragments. And in order to do this IP fragmentation and reassembly, I'll be using these 3 fields, right? Identification, fragment flags, and fragment offset, right? So the first fragment can be of length 1,500, the maximum length that is allowed by the MTU of Ethernet, which is 1,500 bytes. And every IP datagram has an identifier, uniquely identified. So I'll take the identifier and I'll copy all this identifier of larger IP datagram into all the smaller fragments. Why? Because this will indicate that all these 3 smaller fragments are part of a big IP or a larger IP datagram, right? So you can see that I have copied the same identification field in all of these 3 smaller datagrams. And now the situation of flags is, so we have a don't fragment flag, we have more fragment flag here. So don't fragment flag is 1. This means that we do not allow further fragmentation of this smaller datagram. And then more fragment flag is 1 means what? This is not the last fragment of this larger IP datagram, because I'll be sending more fragments as well. And then we have this offset field. And offset field is calculated by dividing the first data byte number by 8, right? Since the fragments must be the fragment size must be the multiple of 8 bytes, except the last one, obviously, right? So let's assume the starting byte number is the data byte number is 0. So I'll divide 0 by 8. Obviously, it's undefined. I'll have the first offset value, which is 0 here. Okay, so I'll discuss in a minute what's the utility of this offset. Okay, so then I'll send the next smaller segment. The length of the next smaller segment can also be of equal to maximum transmission unit size, which is 1,500 bytes. It has the same ID, and the situation of the flags are that don't fragment is 1 and more fragment is also 1. Why? Because, yes, because this is not the last smaller fragment of sequence. And then I have to calculate the fragment offset by dividing the starting data byte number. So here I transmitted how many number of data bytes? It was the total length, by the way, 1,500. So 1,500 minus the header size, which is 20 bytes. So this means the size of the data is 1480. Right? This means it goes from 0 to 1479. So what will be the starting byte number of this smaller datagram? Yes, the starting byte number will be 1480. So I'll divide 1480 by 8 again, and the answer is 185. And then I have this fragment offset of 185, right? And then whatever is left will be encapsulated or will be sent in the last smaller segment. And here the identification field is the same as was the case in the smaller the other smaller datagrams, and the field of the don't fragment or more fragment flags is as given here. So don't fragment flag is set and more fragments flag is 0. This means this indicates the more fragment flag 0 here indicates that this is the last smaller datagram of this IP, larger IP datagram, right? And here the fragment offset is 370. And how it is calculated? So what was the total length that I have transmitted in these two smaller segments? 1500 plus 1500 means 3000, and allow me to minus the header length of these two smaller datagrams, 20 bytes of this smaller datagram and 20 bytes of this smaller datagrams, 40. So this means 2960. And if I start from 0, so the data that I have transmitted so far is from 0 to 2959. So then what will be the starting data byte number here in the last fragment? Yes, 2960. So I'll divide 2960 with 8, and the offset is 370. Right. So in this way, what we have done is we have divided a larger datagram into 3 smaller datagrams, and these 3 smaller datagrams can take different paths to reach the destination. By the way, what is the length of this last datagram? Yes, how? What was the total size that I was supposed to send? Yes, 3980. Why? Because this original larger IP datagram a size of 4000 bytes. So if I minus the header size of 20 bytes, so the total data length would be 3980 bytes. So 3980 bytes minus what? 1480 transmitted in the first minus 1480 transmitted in the second segment. So what this will give me, whatever this will give me, this should give me 1020, right? So this means this is the data length in the last smaller fragment, right? Or datagram. And I'll add 20 bytes of header, obviously, of this last datagram. So the total length would be 1040 here. Right. So now let's assume. So let's assume there's these 3 smaller datagrams take different path to reach the destination and can arrive, as discussed earlier, can arrive out of order. And let's assume that packet smaller datagram number 2 has arrived first. So I need to identify where to place the data that is being carried by or encapsulated by the smaller datagram 2. So what I'll do is I'll multiply the fragment offset by 8. So this means I'll get, so what I'll do is I'll multiply 185 by 8. So I'll get what? Yes, you're right, 1480. So I'll take the data, and the starting byte is 1480, and it will go up to, yes, 2959. And now let's assume that after smaller datagram number 2, datagram number 1 has arrived. So I'll again take the offset and will multiply it by 8. And what is the answer? Yes, 0. So this means I'll place the data inside the IP smaller IP datagram here from 0 to 1479. And then let's assume that at the last we have this fragment number 3. So I'll again take the fragment offset, we'll multiply it with 8, and this will give me 1. Yes, you're right, 2960, right? So the fragment offset helps me to organize or place the data encapsulated by the smaller segment in their appropriate places, right? But there are some problems and complications with this IP fragmentation and reassembly, which is important to be discussed here. So let's talk about the problems with fragmentation and reassembly. Problem with IP fragmentation and reassembly. Why we consider it harmful, right? What? IP fragmentation and assembly. There are different reasons. First, the reason number one is that it complicates routers and end systems. Why? Because now they have to accommodate datagram fragmentation and reassembly. So number one is it complicates the implementation of routers and end systems. Why? Because which need to accommodate IP fragmentation and reassembly. So we are making especially the job of router difficult by by asking it to manage IP fragmentation and especially fragmentation, because reassembly is done at the end machine. Second is that we can create a variety of attacks, right? So for example, we can create a DOS attack because of this fragmentation and reassembly. How? Because the attacker can send series of bizarre and unexpected fragments, right? Which the receiver won't be able to reassemble, right? So the attacker can send a series of bizarre and unexpected fragments, which will create a problem for the end machine to accommodate these fragments. Or we can also come across a problem known as overlapping IP fragments. Overlapping IP fragments means the values of fragments are set in such a way that they do not align properly, right? So fragments do not align properly. Why? Because their values are fragment offsets and other values are set in such a way. But there are other very interesting reasons that I would like to discuss in detail. And say the reason number 3 is, what if I lose one fragment? So if you lose one fragment, what will happen? What do you think? Yes, this means I will lose the whole packet. the larger datagram. And let's try to understand it with the help of an example. Why this happens, by the way? Because kernel has limited buffer space. Number one. Or the second important thing is that IP does not know the number of fragments per packet. IP does not know number of fragments per packet. Right, and let's try to understand this point number 3, which is very interesting, with the help of an example. So let's assume that that a sender sends 2 packets. Sender sends 2 packets, say A and B, and A is fragmented into 8 fragments. So A is fragmented into 8 fragments. And let's assume that the second packet B is fragmented into 2 fragments, smaller fragments, fragmented into 2 smaller fragments, right? And let me also have this condition on the receiver buffer, that the receiver buffer has 8 buffer slots. Receiver has 8 total buffer slots. Okay, and now let's suppose that fragments arrive in the following order. First we have fragment A1, then A2, A3, A4, A5, A6, A7, and then arrives B1, right? And after that, then arrives A8 and the second fragment of the second packet, B2. So what will happen with A8 and B2? A8 and B2 will be dropped. Why? Because we have total 8 buffer slots here, right? Because the receiver's buffer fills up after B1, both packets, this A8 and B2 thrown away, right? And when the reassembly timer times out, this means we have lost the whole packet A and whole packet B. This means the sender has to retransmit this packet A and B. And another very interesting consideration for considering fragmentation harmful is, and this is, we can call it reason number 4, that is inefficient transmission. So fragmentation and fragmentation basically results in inefficient transmission. Let's try to understand this with the help of an example, that how fragmentation results in inefficient transmission. So let's assume, let's try to understand this with the help of example. Let's assume that I have to transmit data of 10 kilobyte. 10 kilobyte of data to be transmitted. And let's assume that TCP let's assume we sent, or this 10 kilobytes of data is sent as 1024 byte TCP segments. So we try to send it as a TCP segment of 1024 bytes. This means we'll be using how many IP packets? Yes, you're right. So this means it uses 10 IP packets to be transmitted from machine A to machine B. And what will be the size of each IP packet? Yes, 1064. So the size of each IP packet is 1064 bytes. How 1064 bytes? What do you think? Yes. So the data size is 1024. So we have 20 bytes of TCP segment header and 20 bytes of IP datagram header. So this will result in 1064 bytes of IP packet, right? And now assume that we want to send it over a link where the maximum transmission unit size is 1006 bytes. So what will happen? Can I encapsulate an IP packet of 1064 bytes into a frame of size 1006 bytes? No, I cannot. So this means what? So this means that each TCP, and this means each TCP fragment or IP datagram will be fragment into 2 packets, right? So this means each TCP packet is fragmented into 2 packets. 2 packets of the packet number 1 will have the size equal to this, the maximum size allowed by this MTU, which is what? 1006 bytes. And whatever is left will be placed in the second fragment. So if I have to send this 1064 byte and I have transmitted 1006 bytes, this means whatever is left plus the 20 bytes header will give me what? 78 bytes. So I'll be sending, this means each of the IP packet will be divided into 2 fragments, one having a size of 1006 and the other having a size of 78 bytes. Okay, so this means if I have to send a data of 10 kilobytes, I'll end up sending. So I will end up sending how many number of packets? Yes, 20 packets. 20 smaller IP datagrams. What if TCP had sent 96 byte segment? Then what? What do you think? What would have changed here in this number? Yes. So in this case, we maybe only need to send 11 packets instead of 20 packets. So that's why it has inefficient transmission, right? So if I would have TCP would have sent 966 bytes of segment, 11 packets were enough to carry this from one end to the other end. So that's why the fragmentation and reassembly, is harmful, right? So this means IP. This means IP does not have control over the number of fragments. Right. So if I want to summarize, so we can say, so what is our analysis here? So number one, IP does not have control over the number of fragments, as we have seen in the previous example here. And the second important thing is TCP can do buffer management because it has more information, right? But this is not happening in fragmentation and reassembly. So TCP can do buffer management better, as we know and we have covered, because it has more information. Since IP has no such information and it has no control over the number of fragments, so this is harmful. But the question is, what is the alternative? What are the alternatives to fragmentation then? So let's talk about the alternatives to fragmentation. Right, so the first possibility is to send only small datagrams. Why not? Send only small datagrams, which are not greater than the maximum transmission unit size. The second possible alternative is to do MTU discovery and let TCP send appropriate segment sizes, right? So we can do what? So we can do path MTU discovery. Why? Because we want TCP to send appropriate segment sizes, or we can set don't fragment flag, right? So do not fragment, and this means our router will not forward the packet because it cannot encapsulate the packet in a specific size of MTU, and it cannot fragment because don't fragment flag is set. So what it can do is it can discard it and send an ICMP error message. Okay. Okay, and most importantly, we can, as an alternative to IP version 4's fragmentation and reassembly, we can have IP version 6, because fragmentation and reassembly is not allowed in IP version 6, because IP version 6 enforces that the minimum MTU should be of size 576 bytes. So this means what? This means no fragmentation at routers. Okay, so this is how fragmentation and reassembly is done, and we've also covered why fragmentation and reassembly is not is considered harmful, and what are the different alternatives that we can make use of. With this, let's talk about IP addressing.